just a sea of people sitting in their kitchens or their spare bedrooms. So it's actually nice to speak to a room full of people. It's actually nice to see that there is a little bit of normality returning, at least in one part of the world. So yeah, it's great that you can all be there together tonight. I just wish I could be there with you. So before I start, I have to recognize the SPE Foundation and its funders, including Offshore Europe, as well as AIME for their support of the Distinguished Lecturer Program. Normally they would pay for the lecturers to travel around the world. It still costs a certain amount of money to put on even the virtual events. And so it's only because of the SPE Foundation and its supporters that we can do this. So as you heard, I'm John Clegg. I left full-time employment in the industry at the end of June, and I'm now running my own consulting business, as you can see on the screen, where I consult on strategy and innovation on a general level, but also as a subject matter expert in drilling. Now, when I wrote this presentation, it takes a while to go through the process of becoming a distinguished lecturer. I actually started writing this presentation early, I think it was March last year, so about 18 months ago. And I did my sort of pitch and at the selection meeting in Calgary in September of last year. And of course, that was all assuming there was going to be an audience there. So it's the first time I've been able to do this, is actually to ask for a show of hands. And I'm just going to ask for a show of hands for a bit of fun, just to get one or two ideas into the conversation, if you like, and then we'll come back to the questions I ask a bit later in the presentation. But I mean, who thinks you can drill a well in a week or less? Sorry, a month or less? Anybody? Yeah, who thinks it might take 3 months or more?
No.
Good start. Okay, and who thinks a well takes I don't know, less than a couple of years to produce? Nobody. And who thinks maybe sort of 5, 10 or more years to produce? How long do you think it takes a well to produce? How long? I mean, how long does it produce for? Who thinks just a couple of years? Yeah, nobody. Who thinks 10 years or more? 5 years or more? Okay, well, yeah. I mean, it's just a bit of fun. Basically, the message is it doesn't take very long at all to drill a well, but once you drilled it, the production should flow for a significant amount of time. And that's a theme that we'll come back to later on in the presentation. So splits into two main pieces, like you should be able to see on the screen. Start by talking about drivers for directional drilling and well placement and how it's done and why people who aren't drillers should be interested, and maybe where it's going to go in the future and how we can influence it. I've got a background in directional drilling, and I think I can say that as directional drillers, we haven't always made things easy for the people that follow us, people that have to worry about completions, and especially people that have to worry about production. And I want to show you why, and finish up by talking about what we might be able to do in the future. But before we go to the future, we'll go back to the past and start and have a look at the history of directional drilling, just to provide a bit of context. And this is a picture, I think this is Huntington Beach in California, and this is some of the first onshore to offshore drilling that was done in the world. This was back in the 1930s. And I'm not going to talk through all of the technologies on this slide, but over 100 years, we've come quite a long way in terms of directional drilling technology, from having simple hardwood wedges to kick off in the 20s, and then that first onshore to offshore well that you saw in the previous picture in the 30s, all the way through sort of bent subs and bent housings for motors, use of stabilizers to enhance directional performance in rotary drilling, then things like MWD, and then rotary steerables, and then unconventionals. When I joined the industry, there were still people who thought it was theoretically impossible to drill a well above 70 degrees inclination, and now we routinely drill horizontals, and some quite long ones. So we've done great things, but I think it's important that in our quest to improve drilling, and directional drilling in particular, we mustn't forget about the reason why we're here. And we're not here to drill a well, but we're here to actually produce from it. So this is a picture of a pump jack, and a lot of people said to me, why do you put up a picture of a pump jack if you're talking about drivers for directional drilling? And the reason is because this production should be the key driver for directional drilling, but I'm not sure that it always is. This is the AFE, or the depth time curve. So we've got depth on the vertical axis and time on the horizontal axis. And as many of us know, the closer this curve is to the left, the less the well costs to drill. And us drilling people, I mean, and I'll put myself in that category, we're kind of obsessed by it. And we do everything we can to try and get that curve as close as possible to the left. But what we don't realize, or maybe what we choose to ignore, is that drilling the well isn't necessarily the best way to optimize the economics of the entire project. There's quite a lot of detail on this slide, so I'll blow it up in a moment to make it a little bit easier to see. It'll still be pretty detailed, but a little bit easier to see. This image comes from a very important paper on surveying and wellbore quality, and it illustrates something known as the Stockhausen effect. It's after one of the authors, a guy called Ed Stockhausen, who is with Chevron, of course. And in its blown up form, you can see it here. And what we've basically got is a graph of inclination on the vertical axis against measured depth on the horizontal axis. So if you're plotting inclination versus measured depth, if you're building angle at a constant rate, then it should be a straight line, the same number of degrees inclination increase per foot or per 100 feet. And moving from bottom left to top right on this graph, you can actually see there is a blue straight line. It's pretty much straight, and that blue straight line is formed by linking together the blue circles that you can see, and those blue circles are inclination that comes from static surveys. That's a survey that you take once you drill the stand and before you start to drill the next one. So it looks great. It looks like we're drilling a nice smooth curve from the MWD surveys. But what was actually happening is that the directional driller was maybe being, taking the easy route. And you can see that from the red dots, and those red dots are continuous inclination readings. And they're not as accurate as the MWD readings, but they give you a good idea of what's going on. And what you can see from those red dots is that after each survey point, the inclination increases quite rapidly until it gets to where it needs to be for the amount of inclination built in that stand. And then it stays horizontal as the DD then rotates to bottom of the stand and gets the right survey result. So what the MWD isn't telling you is there's actually quite a lot of tortuosity in that well, much more than would be apparent from looking at the MWD surveys. And by the way, as a side effect of this, because you get depth from integrating the inclination, there's a very significant TVD error that accumulates over the course of drilling the well. So by the time you finish drilling the well and you think you know where it is and you send your reports into whichever regulatory authority, it's actually a long way from where you thought it was from the MWD surveys. And something else that comes out of Stockhausen's paper is this image, which shows, some people find it hard to see what it is, but it's a piece of rock that's been drilled and then sliced into two. So you're actually looking at a slice through a drilled hole. And the leftmost third of that slice was drilled with a bent housing motor in rotating mode, and the rightmost 2/3 was drilled with it in sliding mode. And you could see that the diameter of the hole drilled rotating is bigger than the diameter of the hole drilled when sliding. And you can see there's a bump, like a step at the transition. And if you're going through a continuous slide rotate, you're going to get that bump appearing at least once every 100 feet or so, at least once every stand. And so imagine that it's like a speed bump. Imagine there's a lot of those speed bumps because you've got at least one every stand. And then imagine trying to run completions or casing into the well. Just like driving along a road with a load of speed bumps, it's going to be more difficult than it needs to be. So there are simple ways to address this, and this is one example, and this is using a rotary steerable system. And so there's a lot going on this slide, but it's actually showing ultrasonic images and ultrasonic caliper details from an ultrasonic imaging tool. The blue plots in the center of each half of the screen show a representation in 3D of the well location and the caliper and the shape of the well bore based on the ultrasonic caliper readings. And just to the right of those, you can see potato plots that show the shape of the well and its relative position relative to the center of the previous slice. And what you can see on the left is a well that was drilled with a directional motor. And you could see that there's a lot of tortuosity there. There's a lot of rugosity. There's a lot of changes in position. It'll be quite a rough sort of hole, and probably it looks like that it's going to be quite a bit less than the bit diameter. And then you look at the one on the right, and it's not perfect, but it's a lot better. And that was drilled with a rotary steerable system. They're both drilled in similar formations, similar locations, similar depth, but it shows, just one small change to the VHA can actually make quite a big difference to tortuosity and wellbore quality. But okay, so you can improve tortuosity. Why does tortuosity actually matter? Why is it a problem? Well, that little show of hands that we had. This is data from IEDC. This is actually from North American wells, but the pattern is the same wherever you go in the world. And they found in 2016, average time to drill a well was 2 to 4 weeks. Average time to complete it is then 3 to 6 weeks. Typical production, anywhere from 5 years to 70 years. So the message there is that compared with the amount of time it takes to drill, the well is around for a long time. So if any sins that you commit in that 2 to 4 weeks when you're drilling a well, they live with you for years or possibly even decades. Now, looking through a slightly different lens, this is an image from the August 2019 issue of JPT, Journal of Petroleum Technology. And it talks about break-even oil prices in different basins in the US and how to get break-even oil prices down. Even more important now than it was when this article was written. And of course, the break-even price is expressed in dollars per barrel. And there's a lot of suggestions in the article about reducing the number of dollars, reducing drilling time, reducing drilling cost. I think it even talked about, trying to push down prices of your suppliers a little bit more, and that's all great stuff. But what was interesting to me is there was nothing in the article about the denominator in that equation, which is the number of barrels. Because if for a given drilling cost, you can increase the number of barrels you get from the well, then for that given drilling cost, you can also reduce the break-even cost. And it's just as powerful a way of reducing break-even as trying to cut down on your drilling costs. And I'll go on to explain why that's important. Just for reference, these are some break-even prices much more recently. This is last month from Rystad, that shows how those US basins fit in with the rest of the world. And similarly, there's going to be opportunity in every one of these applications to reduce break-even, either by reducing drilling costs or by increasing production, just like there was in those basins in the US. And just for a final bit of context, before I start to get into a bit more technical detail, the difference in magnitude between investment and return. And again, this is for a typical US onshore well. The numbers could be very different wherever you go in the world, but hopefully the story is the same, which is that wells are worth more than they cost. So in the US, this was assuming $50 a barrel, but the typical unconventional well is worth about 5 times what it costs to drill. So given the magnitude of those numbers, is it better to try and reduce the cost, or is it better to try and increase the value? So tortuosity is a measure of high frequency deviation from plan, like that kind of wiggliness that you get if things meander rather than going straight from point to point. And there's mathematics that describes tortuosity that's come from looking at things like veins and arteries, which don't tend to go in a straight line, and rivers, which tend to meander as they wander across the countryside. And tortuosity is the measure of how much deviation from that perfection or wiggliness that there is. University of Texas, Austin came up with a definition of tortuosity they called tortuosity index. And I'll look at that in a couple of slides' time. But this was a paper by Apache presented at the 2019 ATCE just over a year ago, showing how in a study they did, if you plot ROP against tortuosity index, where tortuosity was sorted into bins, a low tortuosity index, which means a well with a small amount of tortuosity, is drilled with a significantly higher ROP than one with a large amount of tortuosity. So there's not necessarily a trade-off between ROP and tortuosity. It's just, you know, this is the first indication that it's a good idea to take care about how you drill the wells. And sticking with drilling, this study shows that tortuosity can give an adverse impact on stuck pipe. Maybe that's not surprising, maybe that's intuitive. Stuck pipe can be a problem because you can lose more time than you save by drilling as fast as possible. And what the authors of this paper found is the section leads to fewer drilling problems and higher subsequent well. Is so the well on the and casing standoff, which is shown in red, is pretty consistent. Higher tortuosity, and you can see the casing standoff, which is again shown in red, falls to zero. There's no cement there, and no cement thickness means that you've potentially got issues. This is that definition of tortuosity index from the University of Texas, and probably you'll be as relieved as I am that there's not time to go through and try and derive all the math in here. But it's the important thing on this slide is a conclusion which came out of this particular presentation. And this presentation I took this from came from, and what it showed was a couple of things. It showed that as tortuosity index increases, the average number of rod pump failures per well also increases. And maybe nobody should be surprised about that. You know, if the well isn't straight, it's going to increase the amount of side loading and bending on the rods, and so it will increase the number of failures. The other finding was more interesting, and that is that as the tortuosity index of a well increases, the average initial production decreases. And this is the first time we see there's potentially a negative impact on production from the way that you drill a well. And I'll come back to that in a couple of slides' time. Before I do that, I'll just stick with production equipment. And this is another specific issue with production equipment. This is also uneven, as you'll see from the slide, of an unfortunate electric submersible pump, or ESP, which was landed in a very tortuous section of a well. Now, the tortuosity wasn't visible from MWD surveys, just like with the Stockhausen paper we saw a little while ago. The well looked like it was nice and straight at that point. The MWD surveys weren't able to see the tortuosity in between survey stations. And that was seen later by doing a gyro survey. But based on that MWD survey, this ESP was placed with a view to maximizing production in a particular part of the well. And it worked for 7 days before it failed due to a broken shaft. And the authors say most probably related to excessive bending while operating. And you can see why that might be the case when you look at the shape of well it was in. It's expensive to replace an ESP. It can maybe cost between $250,000 and $500,000, in addition to the lost production time. And I think this again shows what Stockhausen taught us, which is that static surveys don't give you the whole picture. And you really have to understand the tortuosity in between survey stations in your well if you're going to optimize production equipment. But it goes beyond that, and you could talk about production as well. And I kind of wish there was more hard data on production impact than I can show you. And I've come to the conclusion, researching this presentation, that a lot of people don't like to publish SPE papers on how they messed up production by drilling their wells badly. It's not something you probably get the promotion or the bonus for if you, or the incentive for if you produce a paper like that. There was some work that I talked about earlier from UT. There is other work that has been published by universities that shows that there can be significant impacts of tortuosity on production. This is a modeled impact, and this is modeling a horizontal well. The well trajectory is shown in black, and you can see it comes down from the right and lands. And then the lateral is modeled as this sinusoidal undulation with a vertical amplitude of about 50 feet total per cycle, plus or minus 25 feet, which is used to emulate fairly common vertical deviations of a well as you try to hold the set point, which may be 90 degrees or maybe close to 90 degrees inclination. And either the directional driller himself or herself or the directional drilling equipment overshoots and then undershoots as it struggles to get the inclination to exactly the right value. And what happens is that you get these elevation changes, and at the low points you get sumps. And as the well starts to produce, this was an unconventional well, and so you start to get a lot of sand, and the sand starts to settle in the sumps and creates chokes. And over the course of time, these chokes will hold back production. And in this model, you saw significant production hold back after just a month of flowing the well. It's worse with liquids, but that can also happen with gases. It's not going to be a problem with side-to-side kind of snaky undulations, although there could be other problems with those because it still means your well's in the wrong place. But it can be a significant problem with up and down vertical undulations. So I've given you a little bit of a flavor of why tortuosity might be an issue. I'm going to talk now about, well, maybe there are some things that we as an industry could do about it. And indeed, there are some things that we have been doing about it. And so I'll go back in time a few years. I'll talk through recent development of technology, and then I'll project what we might be able to do in the future if we think about things in the right way. So we've been trying to automate directional drilling guidance for a long time. I remember in 1990, Total, I think, were the kind of pioneers and ahead of their time at that time, came up with the first directional drilling advisory system. And that's basically something that told you, given the current well location and the directional target, what tool face setting was required to get to TD. Now, obviously, if you're trying to build or drop in a two-dimensional well where there's no turn, it's easy to calculate the tool face. It's basically either up or down. But if you've got any kind of 3D geometry to the well, it becomes more difficult to calculate intuitively exactly what the tool face could be. And this was the first attempt to do that using a computer system. And we've come a long way since there. And there are now a number of expert directional drilling advisory systems that will tell you what tool face and what dogleg you need in order to get to targets. A bit like the GPS in your car, they'll tell you the shortest, the fastest, the easiest, the route with the least tortuosity, the route that gets you the most production, exposure, and so on. And this is an example of an advisory system augmented with autonomous sliding. And autonomous sliding, that's effectively autonomous control of the tool face at the surface. So rather than the directional driller controlling the orientation of the pipe, the top drive is doing it by itself automatically. And that gives us it doesn't look like a big number, but it is actually quite a significant reduction in sliding percentage in the lateral because we have more precise tool face control. The authors of this paper point out a couple of things. They say, because you're able to autonomously control tool face and reduce sliding, you drill the well a bit faster. But the big benefit that they identify is a much smoother, much more accurate wellbore. So these guys get the value that we're striving for, which is not just drilling fast, but also drilling smooth. And of course, we're automating downhole systems. And this is a paper that I was an author for, but I could have used an example from any of the major service company providers, oilfield service company providers. And in this particular case, a rotary steerable system has got a control loop that controls tool face, but also outside of that, there's a control loop that controls inclination and allows adjustment of bias in the up-down plane where required, so that it can precisely hold inclination to a set value. And so the directional driller can basically take their hands off at that point and just allow the tool to drill to TD, provided the inclination demand doesn't change. And there are also now multiple rotary steerable systems that can control azimuth as well as inclination. And these systems can sometimes struggle at low penetration rates because they don't understand how far they're drilling, and so they can actually put overshoot in at low penetration rates. But at high ROP, like in sort of drilling laterals in the US, they work really well. And this is a first step to downhole autonomy. And I'm going to talk a bit more about automation and what other autonomy we might be able to put into downhole tools in a moment. But before I do that, there's one more piece of existing technology which is in the jigsaw puzzle, and I think that's MPD. And in its simplest form, MPD just allows you to drill without having to stay in that classical mud weight window between pore pressure and formation fracture, as shown on the image. It also allows a lot of other things. It allows kick response, drilling automation, optimization, loss avoidance and loss management, and lots of other things. But for the purposes of automating downhole tools and putting autonomy into downhole directional tools, I'm going to use an analogy, and I'll use a number of analogies over the next few minutes. But in this particular case, if I had been able to come and see you guys today, I'd have flown from London to Bangkok, and I would have done so on a fully automated airplane, an airplane that can take off, fly, and land by itself. And many of us fly, and when we do, we trust our lives to those automated airplanes. And they're perfectly capable of doing it. They're very well tested, and they're very well engineered. But you'd be foolish to jump onto an automated plane without checking the weather. Because if you fly one of those automated planes into a storm, it could end badly. And the same applies here. I don't think you'd be able to develop autonomous drilling systems without thinking about pressure. And so I think MPD, or some sort of pressure management and control, is going to be part of our future of automated and autonomous drilling systems. So the kind of closing section of the presentation starts now. And it starts by asking what's going to happen with automation of the downhole drilling process. And I actually think it's quite unlikely you're going to see an automated system emerge overnight. But I've already shown you one or two pieces of falling into place. And for another analogy, if you think about a modern motor car, it could steer itself if you wanted to stay in lane and follow the white markings on the road. And my car can do that, and it really annoys me. So I actually switched it off because I don't like the car steering itself, but it's capable of doing it. It can follow cars in front at the same speed, and it can brake to avoid hazards and so on. And what we're doing as we drive those cars is we're kind of willingly, maybe unwittingly, testing sensors and subsystems that are going to be necessary for full automation of vehicles. And so that automation is happening gradually, and we're enabling it by trying these systems out as we drive these cars. And I think the same sort of thing is going to happen in drilling. There'll be a gradual process, and we'll continue to see increases in technology like automated top drive control for tool face on a motor, like automated control of direction for a rotary steerable that I just showed you, like directional drilling advisory systems. And these things will gradually accumulate and provide us with more automated systems. I couldn't talk automation without also talking about data. And there's a huge amount of buzz about data, machine learning, artificial intelligence, and so on. I've got a great friend at the Chicago Booth School of Business who wrote a book about AI and artificial intelligence, and talks about how it's been used, especially over the last few years, to develop things like speech recognition, predictive sort of text, dictation systems, and translation systems, and so on. And it turns out that AI is very good, and machine learning is very good for things where there are no rules, like language. I mean, people tried to code language recognition and failed to do so, and gave up about 10 years ago because you just can't write enough code to cover all the special cases. But machine learning is very good at it, and it just works on conditional probability, and it'll look at the context. And if I say the word weather, it'll look at the other words in the sentence to figure out whether I'm talking about rain or sunshine, or whether I'm talking about alternatives, one theory or another. But I think for downhole applications, we're not going to use machine learning in that way because we've still got physics. And we have very good physics models that we've built up over the years. And we shouldn't be throwing those away. And I think we can make data analytics more powerful when we combine it with physics models and use the data to train those models and to fine tune them and to maybe refine some of the assumptions in them. And one recent example of that I worked on is an MPD system where we had a very detailed hydraulics model and we overlaid millions of hours of data onto that model and trained it so it can predict downhole pressure based purely on surface readings. And I think that's how we'll use data in our industry. Optimizing a system, I mean, this is a way of showing you that the target maybe isn't as big as you think it is, because as well as things like wellbore quality, which is the topic of this talk, and things like pressure and ECD, we've got to think about optimizing torque and drag, hydraulics, we've got to manage directional tendencies, we've got to manage drilling dynamics. I think data-based models and improved understanding through data is going to help us to manage a lot of those kind of conflicting boundary conditions and help us to make our future automated drilling systems more successful. But of course, I've talked a lot about directional drilling, and I've shown well paths and well plans and so on. But as we all know, directional drilling isn't about drilling to a set location. There's always geologic uncertainty. As we develop better and better LWD sensors and better interpretation and evaluation techniques, we get much more information about the reservoir as we drill it. This image is from ENI's vision for optimal reservoir management, and this dates back to 2015. And what ENI said in that document is that we can actually quantify the reservoir value as we drill it, or we will be able to quantify the reservoir value as we drill it. So as we drill, we'll be able to use our LWD sensors to give us enough information about what we're drilling to be able to calculate on an incremental basis how much the asset is worth. And of course, we've got geosteering, where we change the direction of the well downhole based on what we learn about the geology and where the reservoir is and how much it's worth and so on as we drill. Geosteering is common and it's well known. But a lot of geosteering is done via a loop through the surface. We send LWD information up to the surface, and then we have computers and then subject matter experts who interpret that data and decide what to do next. And I think our challenge as an industry over the coming decades is to begin to encode that analysis downhole, so that one day you might have a generation of tools that can actually sniff out pay and optimize the value of the well as it's being drilled. And yeah, this is a bit of a dream, just as the title of the slide suggests. But this is a holistic system that I hope, and actually that I expect we'll see at some point in the future. And it's going to be a directional drilling system, probably a rotary steerable, but not necessarily. Could be something else. And that directional drilling system will be capable of responding to required changes in trajectory, just as surely as your car would as you're driving along the road if you turn the steering wheel. But it will have in it multiple formation evaluation sensors, and it will be capable of interpreting those sensors, maybe including imaging sensors downhole, to optimize the trajectory for production. And the first examples of this might be drilling given offset from a bed boundary, or drilling to a given offset from the oil-water contact, and then build out from there. And of course, it'll do all this while minimizing tortuosity, and it'll be able to understand and control how to drill a smooth well. And it'll be in communication with some kind of managed pressure drilling system or some kind of pressure control system to make sure we safely control pressure and don't just give this thing free rein to go and drill wherever it wants and cause havoc. So I'm going to conclude that, say, we've come a long way in 100 years in terms of directional drilling, but in recent times especially, we've become obsessed with drilling very, very quickly. And the question is is drilling faster always better? And my suggested answer is not necessarily. I think sometimes we can compromise wellbore quality by trying to drill too quickly, and I've seen examples of that around the world. The future gives us an opportunity to develop more intelligent automated systems to help us to drill our wells. But I think we need to take the opportunity to make sure that those intelligent automated systems are there to optimize well quality, optimize production, manage well integrity, and not just optimize what happens before TD and get us to TD as fast as possible. And I think our challenge is based on a quote by John DeWart, a friend and colleague of mine, who wrote 3 years ago